Hello everyone. In this video, let's take a look at what shared memory in operating system is. Imagine opening a Google Doc with several other people. Everyone types at the same time and everyone sees the changes instantaneously. So there's person A who writes point A, and then there's also person B who is writing point B, and there are other multiple readers in red which can read any of the data. Everyone is simply looking at the same document in real time. There is no emailing back files or sending any messages. So shared memory in operating systems works in a very similar way. Instead of multiple users, we have multiple processes. And instead of a document, we have a region in memory. And instead of copying data around, all processes directly access the same underlying bytes. Let's take a minute to understand what process isolation is and why sharing is hard. In an operating system, processes are intentionally isolated from one another. Each process runs inside its own virtual address space and behaves as if its own entire machine. This isolation is essential for security and stability. If one process crashes or behaves incorrectly, it should not be able to corrupt the memory of another. However, this same isolation causes an issue because now we cannot make direct memory access from one process to another. Even though two processes may run on the same CPU and use the same RAM, they are not allowed to see each other's memory. To communicate despite this isolation, operating systems provide interprocess communication mechanisms such as pipes, message queues, sockets, and files. These mechanisms rely on copying data. Information is copied from one process into the kernel and then copied again from the kernel into another process. For small messages, this overhead is manageable, but when processes need to exchange large amounts of data such as images, videos, or database pages, this repeated copying becomes a major performance bottleneck and also wastes CPU time and memory bandwidth. Shared memory solves the problem of copying by avoiding it entirely. Instead of moving data between processes, the operating system sets up a mapping so that the same physical memory is visible in multiple virtual address spaces. Once this mapping is established, processes can read and write directly into the shared region. After the initial setup, the kernel largely steps aside. Normal loads and stores go straight to memory without invoking system calls or copying data. This minimizes overhead and allows communication to occur at raw memory speed rather than slower system call speed. In real systems, this zero copy behavior is crucial. Media pipelines use shared memory to pass large video frames between processes without repeatedly copying them. Databases use it to share buffer pages efficiently. In all these cases, shared memory enables extremely high throughput and low latency. A key detail is that the shared memory region does not need to appear at the same virtual address in every process. Each process has its own virtual address space, and those virtual addresses may differ. What makes shared memory work is address translation performed by the hardware. The Memory Management Unit, or MMU, uses page tables to translate virtual addresses into physical memory locations. Different virtual addresses in different processes can point to the same physical memory frame. Shared memory is extremely fast, but speed introduces risk. When multiple processes read and write the same memory at the same time, race conditions can occur. Instructions from different processes may interleave in unpredictable ways, leading to lost updates or inconsistent data. For example, let's say process P1 and P2 are simultaneously trying to increment and decrement a variable x which is in the shared memory, then it might lead to a race condition. Shared memory does not automatically protect against these problems. Correctness depends entirely on the programmer using explicit synchronization mechanisms such as mutexes, semaphores, atomic operations, or read and write locks. Despite its complexity, shared memory is widely used in real systems because of its performance advantages. Databases rely on it for buffer pools. Browsers use it to share cache and resources between processes. Media pipelines use it to move large frames efficiently. And high performance computing systems depend on it for low latency communication. In these scenarios, shared memory often outperforms traditional IPC mechanisms by orders of magnitude, making it the preferred solution when bandwidth and latency matter most. So, to summarize, shared memory allows multiple processes to access the same physical memory, enabling zero copy communication at extremely high speeds. The operating system sets up the mapping, hardware performs the address translation, and process communicates directly through memory. This power, however, requires discipline. Shared memory must be synchronized carefully, and incorrect assumptions can lead to subtle bugs. Thanks for watching.